I am Sridhar Chitta. In this second and final part of two videos, I shall discuss the design and operation of a regulated DC power supply using a unified approach to electrostatics and circuits. I express my sincere thanks to Professor V. Kamaraju, retired Principal and Professor, JNTU College of Engineering, Kakinada, for his valuable suggestions which helped me in structuring the flow of the presentation and enhancing the topics. In this video part 2, I shall discuss the salient subassemblies in a regulated power supply, which includes the operation of the series pass transistor and the means of controlling the voltage drop across the series pass transistor and also overall regulator operation. The astounding speed of operation of the voltage regulator when making adjustments to counter voltage fluctuations is quite amazing, and this I have indicated towards the end of the video before I conclude with an overview of an integrated circuit fixed voltage regulator. In the previous video part 1, I had described the construction and operation of a step-down transformer AC to DC rectification featuring a bridge rectifier, the construction and operation of a capacitor used as a filter, and the generation of an unregulated DC voltage. Certain applications require, especially in areas such as measurement and instrumentation, laboratory level measurements, and in mission critical applications, that the DC supply voltage that powers electronics equipment be steady. In such applications, it will not be possible to use the DC power supply comprising the transformer, rectifier, and filter combination alone, and some means to regulate the output voltage such that it does not vary with variations in the input supply should be incorporated. Such a means would be termed regulation, and the device accomplishing it a regulator. In this video, we shall describe the construction and operation of a 25 volts DC regulated power supply. The animations in the video are useful as an aid to visualize the circuit processes in the operation of the regulated DC power supply. We have not shown the surface charges that are present, which enable the conduction processes in the components for the sake of clarity. It is recommended that the viewer refer to the two videos 1 and 2 listed in the references at the end of this video part 1 of 2, which provide a comprehensive description of the role of surface charges in enabling conduction in electrical and electronic circuits. A series pass transistorized regulator operation encapsulates attributes typically expected from electronic circuits, which are swiftness and extreme elegance that makes the study of electronics so exciting. We will call the output of the filter of the DC power supply, which we described in part 1 of this video set, the unregulated voltage V unregulated. The figure shows the flow of power from the input unregulated voltage to the load, which may be a lamp, signal conditioning circuits of sensors of vital patient parameters in a hospital, signal conditioning circuits of sensors in industrial electronic equipment, or high-end audio amplifiers. Regulation is achieved by using a series pass transistor, the drop across which is controlled through some external means by the amount of base current flowing in it. The purpose of the transistor introduced in series with the load is to adjust the drop across it so that the output of the regulator remains steady in the event of the unregulated voltage fluctuating around some normal voltage when it delivers the desired output voltage. The collector and emitter terminals of the transistor used in such a regulator are connected in series between the filtered output voltage of the DC power supply and the load. The transistor basically operates as an emitter follower. In a few following figures, we show the base of the transistor unconnected for the sake of focusing attention on the collector to emitter voltage only. The figure shows the common emitter collector characteristics of an NPN transistor. We draw a load line corresponding to the filter output voltage VCC equal to V unregulated and the maximum current ICC equal to the filter output voltage divided by the load resistance. The operating point of a transistor is fixed by the amount of base current, say IB5, flowing in it due to a base emitter voltage applied from an external biasing circuit. And the drop across the transistor is given by the collector to emitter voltage VCE at that point. If the unregulated voltage were to increase and the base current were to remain unchanged, a new load line will take effect corresponding to the increased VCC equal to V unregulated. The operating point shifts and the collector to emitter voltage VCE increases and the output voltage increases as well. If the input, that is the unregulated voltage, were to increase, its effect will be felt right around the circuit. The already present electric field zips upward everywhere in the electrical components, and if the base current is unchanged, the voltage across the transistor will increase, but more important, the output voltage will increase too. Note that the electric field is more powerful, shown by long arrows in the transistor and in the resistor. This is so as to uphold the conservation of current law. And if we could somehow further increase the drop across the transistor, we can manage to keep the output voltage from increasing. Because the output voltage is equal to the filtered output, that is unregulated voltage, minus the drop across the transistor. If the unregulated voltage were to decrease and the base current were to remain unchanged, a new load line will take effect corresponding to the decreased VCC equal to V unregulated. The operating point shifts and VCE decreases and the output voltage decreases too. So we see that if the input, that is, the unregulated voltage, were to decrease and if the base current were left unchanged, the already present electric field will weaken everywhere around the circuit. The voltage across the transistor will decrease, but more importantly, the output voltage will decrease too. It should be noted that the electric field in the transistor and in the resistor will be more powerful than in the wires to uphold the conservation of current law. And if we could somehow decrease the drop across the transistor further, we can manage to keep the output voltage from decreasing. Because the output voltage is equal to the filtered output minus the drop across the transistor. A means to vary the voltage drop across, that is between the collector and emitter terminals of the series pass transistor, by controlling its base voltage and so the base current in response to output load voltage variations due to unregulated voltage variation, is the basis of operation of a series pass transistorized voltage regulator. One of the aspects in the design of a regulator using a transistor as the series pass element is that the unregulated voltage must be greater than the desired output voltage. This provides headroom to manipulate the output voltage by varying the base current, by varying the base emitter voltage, should the unregulated voltage fluctuate. If the unregulated voltage were to increase, we arrange for the base current IB5 in our example to be reduced and the operating point further shifts and VCE is increased and the output voltage is restored closer to the desired value. If the unregulated voltage were to decrease, we arrange for the base current IB5 in our example to be increased and the operating point further shifts and VCE is reduced and the output voltage is restored closer to the desired value. The principle of operation of a regulator is the control of the voltage drop between the collector and emitter terminals of a series pass transistor. The transistor should be biased in its active region in order to be able to flex its operation in whichever way desired by its base current. After including the transistor T1 as a series pass element, it has to be biased in the active region. To achieve this, we incorporate a resistor R1 between the unregulated output and the base of the transistor, resulting in a base current IB. We have not shown IC for the sake of clarity. With R1 in place, should the unregulated voltage increase? We note that the V unregulated equals the sum of the VC of transistor T1 and the output voltage. The base current of transistor T1 will increase. and the drop across T1 increases because the load line shifts further, noting that VCC has increased and the operating point moves to a larger VCE. The output voltage will increase and therefore regulation is not possible. A simulation in TINA, which is the simulation software of Texas Instruments, of a circuit gave the following results. Note how the output across R2 and the drop across VCE both increase with increasing supply voltage VCC. If the unregulated voltage were to decrease, once again noting that V unregulated equals the sum of the VC of transistor T1 and the output voltage, the base current of transistor T1 will decrease. And the drop across T1 decreases because the load line shifts further, noting that VCC has decreased and the operating point moves to a smaller VCE. The output voltage will decrease and therefore regulation is not possible. There needs to be a mechanism to divert the base current appropriately should the unregulated voltage increase or decrease. We introduce a transistor T2 for this current diversion task and tie its collector to the base of transistor T1. We now have a handle with which to divert the current from the unregulated voltage to the base of transistor T1. The regulator section incorporates many exciting features of electronic circuit processes: amplification, Zener reference, voltage divider, and feedback. We will step through these as we understand the operation of a regulator. The figure shows the flow of power from the input unregulated voltage to the load. A sample of the output voltage is produced using a voltage divider which permits scaling the sampled voltage. A reference voltage is generated by a current in a Zener diode. An error amplifier compares the two signals, that is, the sampled output voltage and the Zener reference. The amplified error signal controls the amount of current to the base of the series pass transistor, thus adjusting the drop across it. The following design checks are applicable for a regulated power supply. 1. The input rectified unregulated voltage should be greater than the output voltage. You cannot expect to donate 25 apples from 24 apples, can you? 2. The heat dissipation in the amplifying element that drops excess voltage, which must be taken into consideration in the design of a series pass transistorized regulator. The specifications of the regulated DC power supply, which we will describe, are: the input unregulated voltage should be 50 volts plus or minus 5 volts DC. The output regulated voltage should be 25 volts plus or minus 0.5 volts DC. This means the regulated power supply should maintain the output voltage within 24.5 volts and 25.5 volts when the input changes between 45 volts and 55 volts. Current from the unregulated supply will flow in the biasing resistor R1. One part of it will flow to the base of transistor T1 and the other part through the collector of transistor T2. To reduce the current to the base of T1, we may increase the base current to transistor T2. So, more collector current will flow through T2 and the current entering the base of T1 would have reduced, reducing its collector current. Note that the voltage VBE of T1 or T2 will not change perceptibly from about 0.7 volts. To allow more current to flow to the base of T1, decreasing the base current to transistor T2 will cause less collector current to flow through T2. So, the current entering the base of T1 would have increased, thereby increasing its collector current. Note that the voltage VBE of T1 or T2 will not change perceptibly from about 0.7 volts. Decision-making circuitry is now required that will change the voltage of the base terminal of transistor T2 such that the current entering it can be increased should the unregulated voltage increase to divert current away from the base of transistor T1 and thereby increase its drop. Thereby regulating the load, and should the unregulated voltage decrease, then less base current should be made to enter T2 so that the base current to T1 is increased, thereby reducing its voltage drop. Thus regulating the load. To compare changes in the unregulated voltage and so the output voltage as well with the constant reference voltage, a Zener diode is preferred since its voltage Vz is fairly constant. For this, we choose a 15 volt Zener. This is connected to the emitter of transistor T2. A Zener diode requires some amount of biasing current Iz to operate, and this is provided by the resistor Rz that is tied to the output voltage. A fraction of the output voltage is then applied to the base terminal of transistor T2. This fraction that will serve to sample the output voltage and therefore any changes in it is obtained using a voltage divider comprising resistors R2, R3 and R4. Note that the fraction of the output voltage is obtained by using a potentiometer for resistor R3, and this has the advantage of providing a convenient means to adjust or set the regulated output voltage to a fixed value, in our example 25 volts, within some reasonable limit. The deviation or error in the output voltage is sensed and compared by the transistor T2 between the voltage of divider R3 and the reference voltage of the Zener diode. Transistor T2 is an amplifier that amplifies the error caused by a change at the regulator's output voltage, a sample of which we had obtained from the resistor divider. When the unregulated voltage changes, the voltage divider transmits a sample change to the base of transistor T2. The change in the base current of T2 is quite small, and yet it diverts a sizable current IC through itself by the process of amplification. When the input voltage to the regulator is normal, note the ratio of collector to base currents of each transistor. The small base current of transistor T2 controls a large current in its collector emitter. This is amplification. A small amount of power in the base circuit is sufficient to control large amounts of power in the collector emitter circuit. This is similar to manually operating a water valve that lets or blocks large water flows. The unregulated voltage increases to 55 volts. A zip in the electric field is felt at nearly half the speed of light around the circuit. The voltage at the base The voltage at the base of transistor T2 increases due to the increase in output voltage sampled by the network of R2, R3 and R4, and the base current T2 increases. The collector current of T2 increases, and this diverts more current from R1 towards T2 and less current flows to the base of transistor T1. Consequently, the collector emitter voltage of transistor T1 increases to about 29.6 volts. The output voltage settles down at 25.4 volts and 25.4 volts at the load plus 29.6 volts of VCE of transistor T1 is equal to 55 volts of the input unregulated voltage. Watch the speed of action of the circuit of the regulator when the unregulated voltage increases to 55 volts. In reality, it is about 10 to the power of 9 times faster than what you saw. The unregulated voltage decreases to 45 volts and the electric field weakens at nearly half the speed of light around the circuit. The voltage at the base of transistor T2 decreases due to the decrease in output voltage sampled by the network of R2, R3 and R4, and the base current of transistor T2 decreases. The collector current of T2 decreases, and this diverts more current from R1 towards T1 and more current flows to the base of transistor T1. Consequently, the collector-emitter voltage of transistor T1 decreases to about 20.4 volts. The output voltage settles down at 24.6 volts, and 24.6 volts at the load plus 20.4 volts of VCE of transistor T1 is equal to 45 volts of the input unregulated voltage. Watch the speed of action of the regulator circuit when the unregulated voltage decreases to 45 volts. In reality, it is about 10 to the power of 9 times faster than what you saw. It may be noted that the transiting voltage levels between the collector-emitter of transistor T1 and the output voltage indicated when the unregulated voltage changes are for the purpose of illustration of the processes and do not represent actual values in a physical circuit. The actual voltage change levels between the collector-emitter of transistor T1 and at the output and the speed of correction of the circuit will be based on the following parameters of a physically realized operational circuit. 1. The speed of increase or decrease of the unregulated voltage due to line voltage variations. 2. The stray capacitances between circuit elements and across circuit components based on the geometry of the circuit arrangement. 3. The rise and fall times of the collector-emitter voltages of the transistors T1 and T2 in response to their base current changes. A detailed design with calculations for selecting components for a 24 volts DC series pass transistorized regulated power supply can be found in Integrated Electronics by Millman and Halkias and in Electronic Devices and Circuits by Millman and Halkias and Satyabrata Jeet. Commercial voltage regulators are integrated circuit based in 3-terminal configurations and are available for fixed voltages. The popular voltages are 5 volts, 6 volts, 9 volts and 12 volts. Output voltage adjustable regulators are also available, and all the regulators feature additional circuitry for protection from overcurrent. The figure shows the signal and power flow diagram of the popular LM7805 fixed positive 5 volt regulator. As you may note, the regulator features a Zener reference, a transistor error amplifier, and a transistor as the series pass element, which we had discussed earlier. A commercial 7805 regulator incorporates several more transistors than what we had described, and these are necessitated mostly by requirements of ease of fabrication of the regulator on a wafer. The starting circuit provides initial current to the error amplifier circuit so that it does not shut off the series transistor at switch on of the regulator. At switch on, when there is no output voltage and the sampled voltage will be 0, the feedback loop made by the error amplifier may overcorrect and produce output voltage fluctuations, and therefore the starting circuit is necessary. Additional circuitry provides safe operating area protection and thermal protection. The safe operating area curve is a graphical representation of the power handling capability of the regulator under various conditions. The curve takes into account the wire bond current carrying capability, transistor junction temperature, internal power dissipation, and secondary breakdown limitations. The thermal protection prevents damage to the circuit against excessive heating. Thermal protection disables the output when the junction temperature rises to approximately 125 degrees centigrade, allowing the device to cool. When the junction temperature cools down, the output circuitry is enabled. For a link to a video which demonstrates thermal protection, see the description of this part 2 of YouTube. See the description below this YouTube video for a link to part 1 of 2 of this set of 2 videos.